So we're going to review some of the lab items to understand activity a little bit better. So in class we did a demonstration where we had silver ion in solution and we put in a piece of copper metal, so elemental copper, and we waited a while to see what would happen. So over time we observed the results, and what we discovered is that the solution started to turn blue, and that blue is an indication that we are forming copper 2 ion because copper 2 ion is blue in color. Silver ion is colorless. We also saw the formation of a bunch of silvery colored flecks of metal, which is an indication of the formation. Some of it sort of attached to the copper, some of it fell down to the bottom. That's an indication of the formation of silver solid. So when we think about what's happening here, we have copper solid and silver metal. Copper is giving away, first it gives an electron to silver, and then that silver is formed silver solid. But copper really wants to give 2 electrons away, and so it'll find another silver ion to give another silver give another electron to. So to balance the equation, we have 2 silver ions and 2 silver solid atoms on the right. Each copper donates 2 electrons, so that's why it needs 2 silver ions, because each silver ion only takes 1 electron. So here we see that copper is being oxidized and that silver is being reduced. So what we can determine from this is that copper as a metal, this reaction occurs. This reaction occurs in the forward direction, which means the reverse reaction is not spontaneous. It will not occur spontaneously, which means we'd have to put energy in. So we're looking at only spontaneous reactions. We're trying to determine from what reaction occurs which metal, copper or silver, is more active, meaning more reactive in its element form. So because copper reacts, you can assume that silver does not react because the reverse reaction does not occur spontaneously. Then you know that copper is more active than silver as a metal, right? Because you pair it with its ion and it forms the solid silver ion. It's going to form whatever's less active, whatever's more stable. In a second experiment that you did, you took copper ion, copper 2 ion, which is blue. You added solid zinc and you waited for a little period of time, and what you discovered is that the copper solution became lighter in color. That's an indication that copper ion is decreasing in concentration. It's actually being replaced by zinc ion, which is colorless. You also saw some flecks of coppery colored metal, which is copper metal, forming on the outside of the zinc and floating, maybe possibly dropping to the bottom. And what happens in this reaction is that the solid zinc gives away its electrons to form zinc ion. It gives it to copper 2 ion to form copper solid. If the forward reaction occurs, that's why I put the red check here, the reverse reaction definitely does not occur. So that means that zinc as a metal is more active than copper as a metal, because when you mix them together, the zinc will give away its electrons and the copper ion takes the electrons, which means that zinc would rather be zinc 2 ion, copper would rather be copper solid when they're paired together. Now one final reaction that you did, you had acid solution, so XSH+, and you added some zinc metal. And over time you watched what happened, and you observed, hopefully, the formation of some bubbles that appeared probably on the surface of the metal that then maybe rose to the top. Those bubbles are H2 gas. Whenever you see bubbles, it's a sign that a gas is forming. Hydrogen ion will become reduced to form H2 gas, right? It goes from +1 to 0 oxidation state. And those electrons come from the zinc. The zinc gives its electrons to H+ to form H2, and the zinc in turn becomes zinc +2 ion. If the forward reaction happens, the reverse reaction does not happen, which means that zinc is more active than H2 as an element. So I know hydrogen is not a metal, but we usually include it on the activity series. So to summarize the results you should have gotten, this is the lab that you did on activity. The diagonal lines here are X'd out because when we compare the activity of copper solid and copper 2 ion, these are both the same element, which means that there shouldn't be any it's like a tug of war between equally strong people, right? This copper metal will say, oh, sure, you can have these electrons. And then zinc 2 will go, oh, here, have them back. Oh, here, give them here. Oh, give them back. Give them here. Give them back. There's no difference in which one wants the electrons more because they're the same element, right? So all the diagonal lines have been X'd out just to avoid you wasting time trying to watch a reaction that had no free energy. So now when we summarize the results, we have copper 2 ion. All the cations are on the left-hand column, and all of these elements are along the top, right? So this entire column is whether or not copper solid reacts with zinc ion, lead ion, magnesium ion, and H+ ion. So as we summarize the results, if we look at the copper ion solutions one at a time, it should react with zinc, it should also react with lead, it should also react with magnesium. We also can add silver. We know that silver did not react with copper 2 ion. The reverse reaction occurred. So I know that silver is not something you did in your lab. We did this as a demonstration. This X is the only thing we know on the whole table, so we're going to put question marks for everything else. Now if we look at the zinc ion solutions, zinc does not react with copper solid. Now this is something we could have filled in ourselves because we see a check mark here. If zinc solid does react spontaneously with copper 2 ion, then you know that copper solid will not react with zinc ion. So this check alone means that we could have filled this X in. Okay. Now we'll keep going. Lead does not react with zinc ion, but magnesium does react with zinc ion. We don't know about silver. We could guess that it does not because it doesn't even react with copper. Now, again, we have an X here, copper solid and lead ion. We already knew this should be an X because this one is a check, right? So the presence of this check mark means this is definitely going to be an X. This is the forward reaction. The reverse reaction would not occur. Now, if we keep going, lead ion does react with zinc solid, and it does react with magnesium solid. We don't know what would happen with silver, but we could guess that would be an X. Magnesium ion will not react with any of these metals because magnesium ion is very stable. Magnesium solid is very unstable. Hydrogen ion does not react with copper solid, but it does react with solid zinc and solid lead and solid magnesium. Now there should be a question mark here, but my guess is that this would also be an X, right? These would all be X's because silver solid is not going to react with any of these things because solid silver is very unreactive. It has very low activity. It's very stable as it is. That's why we make silver jewelry, because we know it won't become oxidized to silver ion. So we can make our activity series. Magnesium is the most active of the metals that we looked at, followed by zinc, followed by lead. Now we can go back and check our results in terms of copper and hydrogen ion. But here, because copper solid did not react with hydrogen ion, we're going to put hydrogen next. It should be H2 really. And then copper, and then silver is the least active of the ones that we looked at in this lab or demonstration. So here's our activity series. Lithium's at the very top here. And so this is because when you think about reactions of metals, metals tend to lose electrons to form cations. So these are all written as oxidation half reactions, but on the table we write them as reduction half reactions. And so the reaction at the bottom here is the opposite of the reaction we've been looking at. Now if lithium is a very active metal, that means that this reaction that we've written at the bottom is very unlikely to occur. So what you see here at the very bottom, the top is the most likely reaction of a reduction half reaction, and the bottom reaction is the least likely to occur. And so what that means is that in the lower right-hand corner we have a box around lithium metal because that is the strongest reducing agent. If this forward reaction, the way we've written it, lithium plus 1 plus an electron form lithium solid, if that reaction is unlikely, it's very non-spontaneous as written, that means the reverse reaction is very spontaneous. So that's the reaction you see in the activity series, and that's why lithium solid is the strongest reducing agent that we see in this image, because it's very unstable. It wants to give its electron away because it wants to be lithium ion. So a strong reducing agent is something that's very freely giving of its electron. So if you took F2 in the upper left-hand corner and you combined that with lithium solid in the lower right-hand corner, those would react like gangbusters to form lithium fluoride, because fluorine really wants to look like fluoride, and if it could find something to take electrons from, it would do that. Lithium is so freely giving of its electrons, if it could find fluorine, it would love it. It would say, here, take all my electrons. I don't want this electron. I'd rather look like lithium plus 1. Now we're going to practice some practice problems here to make sure everybody understands how to do these. So we're going to do some practice on activity, make sure it all makes sense. Here's the first problem. From the first set of reactions where A does react with the B cation to form the A cation and the B metal, that means that A as a metal is definitely more active than B as a metal, because the forward reaction, if it occurs, we know that the reverse reaction does not occur spontaneously, which means if you're comparing the reactivity of the metals A and B, A reacts whereas B does not when you pair them together. So what that means is that A wants that electron more than B does, right? I'm sorry, A wants to get rid of its electron more than B does. So A gives its electron away to B plus, so that B is going to be the metal. So in terms of their metallic states, A and B, A is less stable than B as a metal. A plus is more stable than B plus as a cation, because those are the products that form. The products are more stable than the reactants. A is more active than B. The second reaction tells you that B is more active than C, because the forward reaction happens, which means the reverse reaction does not happen, which means that B is more giving of its electron than C is. So when you pair them, C will take the electron from B to form the metal C. The last set of reactions, we have B plus the D cation. B is incapable of giving its electron away to D plus, which means that as a metal, B is less active than D, because you know the forward reaction does not occur, which means the reverse reaction does occur. So the reverse reaction would be the metal D giving its electron away to B plus to form B metal plus the D plus cation. So D is more active than B. So we can put them in order of activity. We know that A is more active than B, which is more active than C. But we don't know the location of D. We don't know if D is more or less active than A. So we cannot determine which metal is most active because it's either A or D. So it is not determinable. Which metal is least active? We know that's definitely C. What other reactions need to be performed, if any? We need to compare the activity of A and D. So you either need to pair the metal A with the cation D+. If that reaction occurs, that means A is more active than D. If that reaction does not occur, that means A is less active than D. Or you could pair the metal D with the A plus cation and see if D is capable of giving its electron to A plus. And so if D metal does react with A plus cation, that means that D is more active than A, because you know the reverse reaction would not occur. You could do either reaction, and that would give you the answer. So we have a partial activity series. We're going to predict the placement of cesium. Cesium on the periodic table is in group 1. It's an alkaline metal, just like potassium and sodium. You see the other group 1A metals here. Cesium's not all the way at the bottom, that's francium, but cesium is the next to last element. It's much larger than potassium. So because cesium is larger than potassium, it will be more active than potassium. Its electron is easier to remove. So cesium's down here. So it would be at the top of the activity series because it's much larger. More active than potassium. How would barium's activity compare to cesium's? Now, barium is to the right of cesium. Barium would be less active than cesium because it has a higher nuclear charge. That makes that electron less easy to remove, more difficult to remove. You know that because we compared the activity of sodium, magnesium versus potassium and calcium. Calcium is far less active than potassium, and it's just to the right of potassium here, right? So calcium is here, less active than potassium, and it's to the right. It has a higher nuclear charge, plus 20 instead of plus 19, which makes it more difficult to remove that electron, which is negatively charged. So barium will be less active than cesium. How would francium's activity compare? Francium is even larger than cesium, which means it's easier to remove that last electron. Therefore, it is more active than cesium. It would be above it in the activity series. Now we have our halogens here. If chlorine, this is similar to the activity series for the metals, but instead of talking about the metal activity, we're talking about the non-metal in its elemental form activity. So activity means reactivity when it's in its elemental form, not an ion, but in its neutral form. So that we're talking about the reactivity of chlorine, Cl2, bromine, Br2, fluorine, F2, and iodine, I2. So if we're looking at the first reaction, we see that chlorine will take these electrons away from bromide to form chloride ion and elemental bromine, which means that chlorine as an element is more active than bromine, because just like the metals, if the forward reaction occurs spontaneously, the reverse reaction does not occur spontaneously. So you can say for sure that chlorine is more active than bromine. In the second reaction, fluorine is more active than chlorine. And in the third reaction, iodine is not capable of taking these electrons from bromide, which means bromide wants them more. So iodine is not as reactive as bromine would be, right? So bromine wants those electrons more than iodine does. So you know bromine is more active than iodine. So from these three reactions, we can put these in order of activity. Fluorine is the most, followed by chlorine, followed by bromine, followed by iodine. Next, we're going to look at oxidizing agents. So in terms of oxidizing agents, these are agents that remove electrons the best. They're the best at taking electrons away, which means it's going to be one of these four on the left. The strongest oxidizing agent would be whichever one of these four is best at removing electrons, which means it has to be the most easily oxidized. So from our activity series here, we can see that F2 is the most likely to be oxidized, which means F2 is the strongest, sorry, the most likely to be reduced, which makes it the strongest oxidizing agent. Reducing agents are going to be anything that gives away its electrons, and so that would be the anion forms. So the best is going to be the most active, which is fluorine, for part B. For part C, the most unstable anion is going to correspond, it's going to have a conjugate that is the most stable element. So just like a strong acid has a weak conjugate base, the more stable, and it's the same issue, it's about stability. The more stable I2 is, the less stable I- is. So the weaker I2 is as an oxidizing agent in terms of taking electrons away from something, that's the stronger I- will be as a reducing agent. It's just a measure of how much iodine wants to look like I2 or I-. Which one is better for it? It would rather look like I2, whereas fluorine would rather look like F-. So it's all about stability. So the strongest reducing agent is going to be the one that is best at giving away its electrons. So it's only going to be one of these four, and it's going to be the most reactive anion, which corresponds to the least reactive has the least active conjugate, which is I2. So iodide is the answer to C. Where do you predict astatine would appear in the activity series? It would be the least active because it is, in terms of, it would be last, right, in terms of what am I trying to say? In terms of the trend, right? This is a trend that we see. F2 is more active than chlorine, which is more active than bromine, which is more active than iodine. So clearly astatine goes at the end. That's a trend in activity.